Chapter 3, all about stoichiometry. So at the heart of stoichiometry is dealing with mole ratios. Mole ratios in which, atoms are in a compound, but also mole ratios in which things, compounds react in a chemical reaction. And to start off this chapter, we actually need to introduce 3 types of chemical reactions. You should recognize all 3, and you should also be able to use these to balance reactions as well. That'll be pivotal in getting our mole-to-mole ratios, which is at the heart of stoichiometry. So what do you suppose happens in a combination reaction?
2 elements or molecules combine.
Yeah. So 2 elements or compounds combine to form something new. And the most common ones we'll give you is looking at combining a metal and a non-metal. In fact, one of the ones I give you as a question a little bit is combining aluminum and elemental fluorine. Now, elemental aluminum is monatomic, but fluorine, never have fear of ice-cold beer, is diatomic. And so first thing we got to look at is that. But when you have a metal and a non-metal, what kind of compound do we form between them? Ionic. And you should know the common ion charges. Now for aluminum, he's one of those ones that always has a certain charge. And what was it? Yeah, +3. And then fluorine, like the other halogens, typically in an ionic compound has a -1. So your ionic compound, we got to balance this thing out to where it has no overall charge. If aluminum's +3 and fluorine's -1, how do I make that work? What should be the proper formula for aluminum fluoride here? Good, AlF3, 3 -1s to balance out the 1 + 3. So first we had to predict the product here, but now we need to balance this thing as well. And we're going to follow the rule of customarily trying to avoid having any fractions as coefficients here. So how do I balance this?
2 in front of AlF3.
Cool, put a 2 here. It's kind of hard to get 3 fluorines without using a fraction, so we'll avoid that. So put a 2 here. Now what do I need to do?
2 is 3 is 6, so put a 3 in front of the F.
Good.
2 in front of the Al.
Awesome. So now we've got 2 aluminum atoms on both sides and 6 fluorine atoms on both sides. And there's our balanced combination reaction to form an ionic compound. You should, again, for combination reactions, if it's a metal with a non-metal, you should be able to predict the formula of the product, but also balance this as well. Second kind of reaction you got to be familiar with is decomposition. How does that compare to combination? Yeah, it's typically just the opposite. So it's where you have a compound breaking up into multiple other either compounds or elements. An example might be calcium carbonate. It turns out calcium carbonate doesn't break up into pure elements, but typically will break up into calcium oxide and carbon dioxide. How do I balance this one?
Put 2, put a 2 in front of, no, 3, in front of the CO2.
You sure?
I think so.
It's actually already balanced.
Oh, okay, sure.
Yeah, notice we got 3 oxygens, 1 carbon, 1 carbon, 1. Awesome, awesome. So, but this one, I have 1 substance breaking up into 2 substances, and that's decomposition. Doesn't have to actually break up into pure elements. In this case, breaking up into 2 smaller compounds. Question?
Can polyatomic, I think it was? Yeah, can the polyatomic ions be decomposed into a single S and an O?
So can the polyatomic ions be decomposed into elements like sulfate into S and O? Yes, but it's probably not anything you're ever going to see. So when you start dealing with certain reactions later on and stuff like that, you might see it. Technically, carbonate here was involved in the decomp process here, but just starting out with just carbonate and having it decompose is probably not something you're going to see. It can happen, but probably not something you'll see. Finally, combustion. Why can't I do combustion on the moon? Why can't we do combustion on the moon? Why can't I burn, have a little campfire on the moon?
Oh, because combustion always ends up with water or O2 or CO2.
So it does always end up with water and CO2 for hydrocarbons, although we can actually combust other things like you can actually burn certain metals and stuff like that. But we won't consider it. We'll just be talking about hydrocarbons. But it's not about what you end up with. It's what you need to be able to do combustion, what you start with. And what's not on the moon that you need? Oxygen. Notice that's why one way to put out a fire is to cover it with a blanket because you're cutting it off from oxygen. So combustion always involves reacting something with oxygen. Oxygen's the other reactant. And you should realize how to do combustion reactions for specifically compounds that contain mostly just carbon, hydrogen, or maybe carbon, hydrogen, and oxygen. So the one on your handout we're going to do, Write a balanced reaction for the combination. Nope. What are the products of the combustion of C3H8 and balance that reaction? So in this case, C3H8 just happens to be propane. And we're going to write out the combustion reaction. So it's just a hydrocarbon. It only contains hydrogen and carbon. It could have also contained oxygen, and we could still do it. Anything else is nothing you're responsible for at this stage of the game, although we can do combustion of other things as well. But the key is this. This is the variable part in a combustion reaction. The set parts is O2 is always the other reaction, or reactant, I should say, and that CO2 and water are always your products.
The O always have to be diatomic.
So, and it's O2 gas, the diatomic elemental oxygen for a combustion reaction, for sure. So in this case, again, these three parts are all fixed. It's just what's the thing you're combusting. That's what's going to be variable here. And you got to balance it. Now, this is where balancing gets a little more challenging, definitely more than the last one we did here. So, but what makes this challenging is if you pick the wrong element to balance first, you are hosed. And the wrong one to choose here is oxygen. And the way you recognize that it's the wrong one to choose, any element that shows up on one side of the arrow in more than one compound, don't choose him. And oxygen shows up in both products. Skip it. Don't balance him. He's the last thing you want to balance. So in this case, though, carbon only shows up in one compound on the reactant side and one on the product side. Hydrogen only shows up in one compound on the reactant side and one compound on the product side. Either one of those would be a great place to start. Where do you want to start?
Let's do I did a 3 in front of CO2.
Awesome. Let's balance the carbons by putting a 3 in front of CO2.
And 2 in front of the C3H8.
So you put a 2 there, though. If you put a 2 there, then you'd have to put a what there?
True.
So let's not do that. So, but notice we can balance the hydrogens right off the bat anyways. How many hydrogens we got on this side? 8. How do I make sure I get 8 on that side?
4.
Awesome. We'll put a 4 here. And now, because these coefficients are set, now I can put a coefficient in front of O2 and balance the oxygen. So how many O atoms do we have on this side?
It's a 3.
So we got 6 O's there, 4 O's there. That's a total of 10 O's. So how many O2s do I need? Awesome. And we'll put a big fat 5 right there. And now we've got a balanced combustion reaction for C3H8. So if we say combustion, you're supposed to know, oh yeah, O2 is the other reactant and CO2 and water are the products. And then you should be able to balance it, balance carbon and hydrogen before you balance oxygen. Cool. The rest of the night, we're going to be dealing with moles. And Natalia, I know we talked about this the other day, so I know you know what a mole is. What's a mole?
A mole is like the 6.0.
Yeah, it's 6.02 times 10 to the 23rd. It's a number. Notice if I said I have a dozen eggs, how many eggs do I have? I got 12. If I have a baker's dozen of donuts, how many donuts do I have?
13, because the baker always gets 1.
Yes, 13, because the baker makes 12 for the customer and 1 for the baker. Sweet. And in the same way, a mole is just a number. It's just a much larger number than a dozen or a baker's dozen. It's 6.02 times 10 to the 23rd. And it's such a big number because atoms and molecules are so tiny. So if I have a mole of eggs, what would that look like? What would a mole of eggs look like?
0.02 times 10 to the 23rd.
Well, it would be that many eggs, but what would that actually look like? Like, would that fill up this room?
That would be like a couple hundred miles tall.
Yeah, it would probably be enough eggs to cover the entire Earth, like to a depth of meters or miles or who knows how far. But it would be a ton of eggs. So we'd never talk about that many eggs. That many eggs doesn't even exist, right? So, but we can talk about that many molecules and atoms. If I had 6.02 times 10 to the 23rd water molecules, that would be enough to fit in a very small cup of water. So molecules and atoms are super tiny. And if we don't talk about very large numbers of them, so then we wouldn't have enough to actually see or play with our hands and stuff like that. That's why we're dealing with these big numbers. So a mole is just a number. You should understand that first and foremost. If I talk about a mole of eggs, it's that many eggs. A mole of donuts, it's that many donuts. Now, we would never talk about eggs and donuts with that number, but if I say this many carbon atoms, or a mole of carbon atoms, you should know it's this many carbon atoms. A mole of water molecules, it's 6.02 times 10 to the 23rd water molecules. A mole always, always, always means a number. Cool? Now, as long as you're on the periodic table, somebody was nice enough to go out and weigh 6.02 times 10 to the 23rd of every single atom and published it right here. the atomic mass in the periodic table. So if I have 1 mole of carbon atoms, how many carbon atoms is that again?
12.01.
No, that's not the question I asked, actually. How many carbon atoms is it if I have a mole? 6.02. But how much does it weigh? What's its mass? 12.011 grams. So that's the connection here. So a mole always tells you how many of something you have, but if it's on the periodic table, you can also figure out how much it weighs, what its mass is in grams as well. So that's what's kind of nice. Now, one thing to note, they'd said, wouldn't it be nice? 6.02 times 10 to the 23rd carbon atoms weighs 12.011 grams. That's fantastic. What would one atom weigh? Well, they're like, okay, well, 12.011, for all those atoms, if I divide by 6.02 times 10 to the 23rd, that would be 1 atom. And that would be a super tiny number. So they said, let's not weigh that in grams. If we weigh 1 atom, let's make up a new unit and just call it the atomic mass unit, and it would be the same number. And so they did. And so if you have 1 carbon atom, rather than getting this super tiny mass in grams, they just say that it weighs 12.011 AMUs. So now this actually means 2 things. This gives you the mass of 1 atom in AMUs, or it gives you the entire mass of 6.02 times 10 to the 23rd atoms in grams. So in this case, if it's 1 atom, we call it the atomic mass. If it's an entire mole of atoms, 6.02 times 10 to the 23rd atoms in grams, we would call that the molar mass. And we use those pretty interchangeably, even though one of them is really for 1 atom, and one of them's for an entire mole of atoms. But one of them's in AMUs, one of them's in grams, but it's the same number either way. So whether we say atomic weight or molar mass, use that number. Cool. Let's have a little fun with this. You have 12 grams of carbon, diamond in this case. How many moles of carbon do you have? Yeah, essentially that's the mass of 1 mole. And in this case, we would say, 1 mole of carbon weighs 12 grams. And the connection between grams and moles is always the molar mass on that periodic table. Look at right off of there. And so in this case, our grams cancel, and we find out that we've got, 1 mole of carbon atoms. Now, the next question, though, is how many carbon atoms do you have? Well, 1 mole is always 6.02 times 10 to the 23rd, and that's where you'd use Avogadro's number as your conversion here. So 1 mole is always 6.02 times 10 to the 23rd of whatever you're talking about, in this case, carbon atoms. Now we've got to be a little careful, because now we've just seen that there's a connection between moles and grams, the mass, but there's also a connection between moles and the number of, say, atoms or molecules, the number of whatever you're talking about. So now the definition of moles is what gets you to the number of something you have. The only reason we can get to the grams of something is because somebody was nice enough to publish it on the periodic table. So if I said, what does 1 mole of carbon weigh again? We get 12 grams. What does 1 mole of neon weigh?
20.17.
So I'll round it to 20 grams. So on and so forth. What does 1 mole of donuts weigh? A lot. Good. You don't know the exact number because it's not on the periodic table. If somebody made a nice little square cutout for donuts on the periodic table and published the data, we'd know exactly how much a mole of donuts weighs. Otherwise, if we knew the average weight of 1 donut, we could then take that average and multiply by 6.02 times 10 to the 23rd and figure it out. But because it's not on the periodic table, we don't know it right off the bat. But as long as it's on the periodic table, somebody's published the connection here, and we're good to go. But because there's this connection between moles and grams and moles and the number of something, students often get confused on what's being asked. So if I asked my mom, how much do you weigh, Mom? And she says, 60 years old. I'm just going to look a little confused. And if I ask my mom, how old are you, Mom? And she says 110 pounds. I'm going to look really confused because she's not answering the question I'm actually asking. The same thing happens here. If I tell you have a mole of carbon atoms, if I ask students how many atoms there actually are, they should be going here. And oftentimes, unfortunately, they'll tell me 12 grams, and they've answered a different question than the one asked. And sometimes vice versa. If I say, you have 1 mole of carbon atoms, how much do they weigh? Instead of telling me the grams, they give me Avogadro's number instead, and they're answering a question I didn't ask. So definitely want to get good at recognizing what you're actually being asked so you can convert back and forth there. So there's this connection between grams and moles and a connection between the number of atoms and moles, but there's not a connection between grams and the number of something directly. You have to go through moles to get there. So there's the phrase, all roads lead to Moleville. So you can convert between moles and anything, essentially. So if you need to do a conversion and you don't have moles, probably the first thing you'll do is get there. Let's have a little more fun with this. Cool, for the next 3 questions, they are all based on the fact that we have 196 grams of H2SO4. The series of questions we are going to answer, the first one is, how many moles of H2SO4 do we have? How many oxygen atoms are in the sample? And then how many grams of hydrogen atoms are in the sample? Let's start with the first one. How many moles of H2SO4 do we have? How do I convert grams to moles? What's my connection?
Grams to moles. Molar mass.
By the molar mass. Where do I always get the molar mass? On the periodic table. So what does 1 mole of H2SO4 actually weigh?
98 grams.
98 grams. Sweet. 2 hydrogens, that's 2 times 1. Sulfur is 32, so plus 32. And then 4 oxygens is 4 times 16, so 64. And indeed, it does weigh 98 grams. So 1 mole of H2SO4 on top, 98 grams of H2SO4 on bottom. That way our grams cancel. And so how many moles of H2SO4 do we actually have?
You would take 98 divided that by 196,
Awesome.
sorry. 0.5, so half of 1.
Ooh, you got it actually backwards. It's actually 196 over 98, right? So instead of 1/2, it's 2 over 1 or 2.
2.
Awesome. Cool. And now that we know we have 2 moles of H2SO4, we can take advantage of some mole ratios here. So again, at the heart of stoichiometry is mole ratios, or R mole ratios, I really should say properly. In this case, H2SO4, when you have 1 mole of H2SO4, you have 2 moles of hydrogen atoms, 1 mole of sulfur atoms, and 4 moles of oxygen atoms. It's a ratio, no matter how you look at it. So in this case, let's take this a couple of different places. How many, if we have 2 moles of H2SO4, how many moles of hydrogen atoms do we have?
2.
Is it 2?
2 moles of H.
We have 2 moles of H2SO4, so awesome. Every one of these has 2 moles of hydrogen atoms, so if we have 2 moles of H2SO4, we have 4 moles of H atoms. Cool, how many moles of sulfur atoms?
2.
Good, only 1 sulfur per H2SO4, so 2 moles of H2SO4 is 2 moles of sulfur atoms. And finally, how many moles of oxygen atoms?
8.
Awesome, 8 moles of oxygen atoms. Now, having the moles of each of these, what are the 2 things I can convert moles to?
Grams.
Grams or the numbers of atoms or molecules or whatever. So in this case, having the moles of each of these, I could turn each one of these into a mass of those atoms or into the number of atoms. Take your pick. So, and the first one we want to do is how many oxygen atoms are in the sample. So we are going to base that right off of this number here. We have 8 moles of oxygen atoms, and that's what I need to know to be able to turn that into just the absolute number of oxygen atoms. And what's my connection between moles and the actual number of something? It's Avogadro's number, yep. And so in this case, we will put moles of oxygen atoms on the bottom, and we'll just put plain old number of oxygen atoms on top. And 1 mole always has 6.02 times 10 to the 23rd of whatever we're talking about. And so in this case, we have 8 moles, and each mole is 6.02 times 10 to the 23rd atoms, so how many total do we have?
4.81 times 10 to the 24th.
Good, 4.81 times 10 to the 24th oxygen atoms. Life is good. Fantastic. Next question you're asked is about the mass of hydrogen atoms. So how many grams of hydrogen atoms are there in the sample? So again, if we're talking about the grams of hydrogen atoms, it's convenient to start with moles of hydrogen atoms to get there. So in this case, what's my connection between moles and grams again?
The atomic weight. So
Yep, atomic weight or molar mass. Sweet.
1 per hydrogen atom.
Awesome. So we'll put moles of hydrogen atom on the bottom, grams of H atoms on the top, and 1 mole weighs 1 gram for hydrogen. That's convenient. And so 4 moles of hydrogen atoms weighs 4 grams. And that's the answer to our next question there. Life is good. Cool, so this is again really at the heart of stoichiometry. The heart of stoichiometry is ratios. 1 H2SO4 contains 2 H's. 1 H2SO4 contains 1 sulfur. 1 H2SO4 contains 4 oxygens. And whether you look at that as 1 molecule versus 2 hydrogen atoms, or 1 mole of H2SO4 versus 2 moles of H, same diff. And we will much more commonly use these mole-to-mole ratios.